Welcome! In this session, we'll delve into problem number 210, Course Schedule 2. This is a fascinating problem that explores topological sorting to determine the order of course completion based on prerequisites. Together, we'll analyze the problem, discuss various approaches, and learn how to solve it efficiently. Let's get started. The problem we're solving involves determining the order to take a set of courses, given their prerequisites. You are provided with a total number of courses, labeled from 0 to number courses 1. Along with this, you are given a list of prerequisites, where each prerequisite is represented as a pair, A, B. This means that to take course A, you must first complete course B. Your task is to return an array that represents the correct order in which these courses can be taken to finish them all. If it's not possible to complete all courses due to contradictory prerequisites, you should return an empty array. The input consists of two parts, number courses, an integer representing the total number of courses, and prerequisites, a list of pairs specifying the dependency relationships between courses. The output should be an array that satisfies all prerequisites or is empty if no valid order exists. Let's look at some examples to better understand the problem. In the first example, we have number courses equals 2 and prerequisites equals 1, 0. This means that to take course 1, you need to complete course 0 beforehand. The result, in this case, is 0, 1, indicating that you should first take course 0 and then course 1. In another example, where number courses equals 4 and the prerequisites are 1, 0, 2, 0, 3, 1, 3, 2, the output is 0, 1, 2, 3. Here, the dependencies show that both courses 1 and 2 need course 0 to be completed first, and course 3 depends on both courses 1 and 2. This ordering satisfies all the prerequisites. Breaking down the second example further, we can see how each dependency is fulfilled. To take course 1, course 0 must be completed first. Similarly, course 2 also depends on course 0. For course 3, you need to complete both courses 1 and 2. One valid order that satisfies these conditions is 0, 1, 2, 3. However, other valid orders, like 0, 2, 1, 3, also exist because course 1 and course 2 can be taken in either order after course 0. In a simpler case, if there's only one course, such as number courses equals 1 with no prerequisites, the output is straightforward, the only valid order is 0, since there are no dependencies. Now consider a scenario where it is impossible to complete all courses. For example, if number courses equals 2 and prerequisites equals 1, 0, 0, 1, the prerequisites form a cycle, course 1 depends on course 0, and course 0 depends on course 1. This circular dependency makes it impossible to complete either course, so the output is an empty array. Finally, let's review the constraints for this problem. The number of courses, number courses, can range from 1 to 2000. The prerequisites list can have a maximum length of number courses asterisk, number courses 1, and each prerequisite pair contains exactly two values, A and B, where both are valid course indices ranging from 0 to number courses 1. There are a few important points and edge cases to consider. First, if there are no prerequisites, any order of courses is valid since there are no dependencies to satisfy. Second, when there is only one course, like number courses equals 1, the result is simply 0. Because there are no other options. Third, if the prerequisites contain a cycle, it becomes impossible to complete all courses, and the output should be an empty array. Lastly, in cases where the courses form disconnected groups with no dependencies between them, multiple valid orders are possible, as each group can be completed independently. Additionally, all pairs in the prerequisites list are unique, ensuring that no redundant dependencies exist. When tackling the Course Schedule 2 problem, we first considered the brute force approach using backtracking. The idea here is to generate all possible orders of courses and check each one to see if it meets the prerequisites. For every course in a sequence, we would ensure all its prerequisites appear earlier. While this approach is straightforward, it comes with a major downside. Generating all permutations of the courses has a factorial time complexity, which means it becomes computationally infeasible as the number of courses increases. Verifying each permutation adds even more overhead, making this method impractical for large inputs. While it might work for very small numbers of courses, it doesn't scale effectively. On the other hand, a more efficient approach involves treating the problem as a graph and solving it using topological sorting. This is because the problem can be seen as finding a valid order of tasks based on their dependencies, which is a classic graph theory problem involving a directed acyclic graph, or DAG. In this representation, courses become nodes and prerequisites are the directed edges between them. To solve the problem using topological sorting, the first step is to represent the course prerequisites as a graph, typically using an adjacency list. Next, we compute the integrity of each node, which represents the number of incoming edges, or in this case, the number of prerequisites for each course. Once we have this information, we can then apply one of two algorithms, Kahn's algorithm, which is a BFS-based approach, or a DFS-based topological sorting method. For this problem, we focus on Kahn's algorithm due to its simplicity and efficiency. The steps for Kahn's algorithm begin with constructing the graph. Then, we calculate the integrity for each course and initialize a queue containing all nodes with an integrity of 0. These are the courses that don't have any prerequisites and can be taken immediately. From there, we process each node in the queue, add it to our result, and reduce the integrity of its neighbors. If any neighbor's integrity becomes 0, we add it to the queue as well. This cycle continues until all nodes are processed. If we process all nodes successfully, we return the result as the valid course order. However, if any nodes remain unprocessed, it indicates the presence of a cycle, meaning no valid ordering exists. Analyzing the efficiency, Kahn's algorithm has a time complexity of O, V plus E, where V is the number of courses and E is the number of prerequisite relationships. This efficiency comes from the fact that each node and edge is processed exactly once. The space complexity is also O, V plus E, primarily due to the adjacency list used to represent the graph and the queue for processing nodes. Alternatively, there's the DFS-based approach for topological sorting. In this method, we use a visited array to track the traversal state of each node. Nodes can exist in three states: unvisited, visiting, and fully visited. A key step in the DFS approach is to detect cycles by revisiting nodes that are still in the visiting state. If a cycle is detected, we return an empty list since no valid order can exist. Otherwise, we add nodes to the result list in reverse order of their DFS finish times. At the end, reversing the result gives us the correct topological order. Like Kahn's algorithm, the time complexity for DFS is O, V plus E, due to similar reasons, and the space complexity is also O, V plus E, accounting for the graph representation and the recursion stack. Representing courses and prerequisites as a graph transforms the problem into a more structured task. Topological sorting ensures that prerequisites are completed before the courses that depend on them, directly addressing the problem's requirements. Kahn's algorithm, or the BFS-based approach, is particularly intuitive because it works by iteratively removing courses with no remaining prerequisites. On the other hand, the DFS-based method leverages recursion to build the topological order in reverse. One of the reasons we favor Kahn's algorithm is its iterative nature, which makes it easier to debug and avoids the potential pitfalls of recursion, such as stack overflow in deep graphs. Additionally, Kahn's algorithm naturally incorporates cycle detection by checking if all nodes are processed. If any nodes remain, it means there's a cycle. This simplicity, combined with its space efficiency, makes it a strong candidate for this problem compared to DFS. When comparing the trade-offs between DFS and BFS for topological sorting, both are efficient and have the same time and space complexities. However, BFS through Kahn's algorithm tends to be more intuitive for developers, as it doesn't rely on recursion or reverse postorder traversal, which can feel less straightforward. Additionally, Kahn's algorithm handles cycle detection more explicitly by verifying if all nodes are processed. Both approaches handle edge cases well, such as disconnected graphs or situations where no valid ordering is possible. Ultimately, we chose Kahn's algorithm due to its clarity, ease of implementation, and natural ability to detect cycles. It is highly scalable and works efficiently within the constraints of the problem, making it an excellent choice for solving course schedule 2. To solve the problem, we need to determine if it's possible to complete all the courses in a curriculum, given a list of prerequisites. Each course has specific requirements that must be fulfilled before it can be taken, and our goal is to find an order in which all courses can be completed, or conclude that it's not feasible. A basic approach to understand this problem is brute force backtracking. In this method, we generate every possible order of taking the courses and verify whether any of these orders satisfy the prerequisite conditions. To begin, we represent the courses as integers from 0 to n1, where n is the total number of courses. The prerequisites are modeled as a directed graph, where an edge from course U to course V indicates that U must be taken before V. We use an adjacency list to efficiently store this graph, where each course points to the list of courses dependent on it. The next step is to generate all possible permutations of the courses. Since there are n courses, this results in n factorial permutations. Using a backtracking function, we systematically create these permutations. For each permutation, we then validate if it satisfies all the prerequisite conditions. To validate, we iterate through the courses in the given order of the permutation, keeping track of completed courses using a set. For each course in the permutation, we ensure that all its prerequisites exist in the set of completed courses. If a prerequisite is missing, the permutation fails the validation. Once all permutations are checked, if a valid one is found, we return it as the course order. Otherwise, we return either an empty list or a false value, indicating that completing all courses is not possible. For example, consider a scenario with 3 courses and prerequisites like 0 must precede 1, and 1 must precede 2. This can be represented as prerequisites 1, 0, 2, 1. In this example, the graph representation for the prerequisites would be 0, 1, 1, 2, 2. Next, we generate all possible permutations of the courses, which could include orders like 0, 1, 2, 0, 2, 1, 1, 0, 2, and so on. For each permutation, we systematically check if it satisfies the prerequisite conditions. For instance, the order 0, 1, 2 is valid because 0 comes before 1 and 1 comes before 2. On the other hand, the order 0, 2, 1 fails because course 2 is attempted before course 1, which violates the prerequisite that 1 must come before 2. Once we identify a valid permutation, such as 0, 1, 2, we output it as the solution. This example highlights the brute force nature of the backtracking approach, which checks all possibilities exhaustively. However, the factorial growth of permutations makes this method highly inefficient for large inputs, underscoring the need for more optimized approaches. To implement this algorithm effectively, the adjacency list and set play crucial roles. The adjacency list allows us to store the prerequisite relationships in a way that provides constant time access to the prerequisites for any course. Meanwhile, the set dynamically tracks which courses have been completed, enabling quick validation of prerequisites during the permutation checks. However, the inefficiency of this approach lies in its complexity. Generating n factorial permutations requires O(n), and validating each permutation takes O(n), leading to an overall time complexity of O(n). (n). Additionally, the space complexity is O(n), due to the recursion stack used in the backtracking process and the set used for validation. To address these inefficiencies, we can transition to graph-based methods like topological sorting. Algorithms like depth-first search or Kahn's algorithm can significantly reduce the complexity to O, V plus E, where V is the number of courses and E is the number of prerequisite relationships. These optimized approaches are far better suited for large-scale problems. Here, we start by importing the necessary modules, defaultDict and deque, to handle the graph representation and queue operations efficiently. The findOrder function begins by constructing an adjacency list to represent the course prerequisites as a directed graph. We also initialize an in_degree array to track the number of prerequisites for each course. For every prerequisite pair, where src is the prerequisite for dest, we add dest to the adjacency list of src and increment the in_degree of dest. Next, we identify all courses that have no prerequisites, which means their in_degree is 0. These courses are added to a queue, as they can be taken immediately. The result list is initialized to store the final order of courses. Then, we process the courses in the queue one by one. For each course, it is removed from the queue and added to the result list. We then reduce the in_degree of its neighboring courses, as one of their prerequisites has now been fulfilled. If a neighboring course's in_degree becomes 0, it is added to the queue for processing. This process continues until all courses with 0 in_degree are handled. After processing all nodes, we need to verify if the result list contains all the courses. If the length of the result equals the total number of courses, it means we have successfully found an order in which all courses can be completed, and we return the result. Otherwise, if there are still courses left unprocessed, it indicates that there is a cycle in the graph, making it impossible to complete all courses. In such cases, we simply return an empty list. Here, we start by implementing the solution in Java. The method findOrder takes the number of courses, and an array of prerequisites. The first step is to build an adjacency list to represent the course dependencies and an array to track the indegrees of each course. The adjacency list, graph, is initialized as an array of lists, where each course has its own list of dependent courses. Then, as we iterate over the prerequisites, we populate the adjacency list and increment the indegree for courses that have prerequisites. Once this setup is complete, we initialize a queue to keep track of courses with no prerequisites, i.e., courses that have an indegree of 0. These courses can be added to the queue immediately since they have no dependencies blocking them. Next, we process the courses in the queue. We initialize a result array to store the order of courses and an index variable to keep track of our position in the result array. While the queue is not empty, we dequeue a course, add it to the result array, and decrement the indegree of its neighbors in the graph. If any of these neighbors now have an indegree of 0, they are added to the queue since their dependencies have been resolved. Finally, after processing all courses, we check if the result array contains all number courses. If it does, we return the result. Otherwise, if there was a cycle and not all courses could be completed, we return an empty array. To solve this problem, we start with a basic case where there are 2 courses and a single prerequisite. The input indicates that course 1 depends on course 0. First, we create an adjacency list to represent the graph and an indegree array to track the number of prerequisites each course has. The adjacency list is initialized as an empty dictionary, and the indegree array begins with zeros for each course. When processing the prerequisite 1, 0, we add course 1 to the adjacency list of course 0 and increment the indegree of course 1. This gives us a graph where course 0 points to course 1, and the indegree array shows that course 1 has 1 prerequisite while course 0 has none. Next, we identify all courses with no prerequisites by looking for courses with an indegree of 0. Here, only course 0 qualifies, so we add it to the queue, which is now ready for processing. Now, we begin processing the courses in the queue. First, we remove course 0 from the queue and add it to our result list, indicating that it can be taken. Since course 0 has a neighbor, course 1, we reduce the indegree of course 1 by 1, signifying that one of its prerequisites has been satisfied. This update makes the indegree of course 1 0, so we add it to the queue. Next, we remove course 1 from the queue and add it to the result list. At this point, the queue is empty, and our result list contains 0, 1. Finally, since the length of the result list matches the total number of courses, we confirm that all courses can be completed, and the result, 0, 1, is returned. This represents a valid order to complete the courses. In a more complex example with multiple dependencies, we have 4 courses and several prerequisites. The input specifies that course 1 and course 2 both depend on course 0, while course 3 depends on both courses 1 and 2. To start, we create the adjacency list and indegree array. The adjacency list is initially empty, and the indegree array is filled with zeros. As we process each prerequisite, such as 1, 0, we update the adjacency list to reflect the dependency and increment the indegree of the dependent course. Repeating this for all prerequisites results in a graph where course 0 points to courses 1 and 2, and courses 1 and 2 both point to course 3. The indegree array now shows that courses 1 and 2 each have 1 prerequisite, while course 3 has 2, and course 0 has none. At this stage, we identify courses with no prerequisites by checking for an indegree of 0. Only course 0 qualifies, so it is added to the queue for processing. We proceed to process the courses in the queue. First, course 0 is removed from the queue and added to the result list. Its neighbors, courses 1 and 2, have their indegrees reduced by 1. Since this makes their indegrees 0, both are added to the queue. Next, course 1 is removed from the queue and added to the result list. Its neighbor, course 3, has its indegree reduced by 1, but it is not yet added to the queue because its in-degree is still greater than 0. Then, course 2 is removed from the queue and added to the result list. This time, reducing the in-degree of course 3 makes it 0, so course 3 is added to the queue. Finally, course 3 is removed from the queue and added to the result list. At this point, the queue is empty, and the result list contains 0, 1, 2, 3. Since the result length matches the number of courses, we confirm that all courses can be completed in this order. The output for this example is 0, 1, 2, 3, which represents a valid order for completing the courses. However, not all inputs guarantee a valid course order. For instance, consider a case where the prerequisites form a cycle. With two courses in prerequisites indicating that course 1 depends on course 0, and course 0 depends on course 1, we begin by creating the adjacency list in in-degree array. After processing the prerequisites, the graph shows that course 0 points to course 1, and course 1 points back to course 0. The in-degree array indicates that both courses have one prerequisite, meaning there are no courses with 0 prerequisites. As a result, the queue remains empty, and no courses can be processed. When the queue is empty and no courses have been processed, the result list remains empty. Since the length of the result list does not match the total number of courses, we conclude that it is impossible to complete all the courses. This happens because the prerequisites form a cycle, creating a deadlock where no course can be taken first. The output in this case is an empty list, indicating that there is no valid order to complete the courses. This highlights the importance of detecting cycles in the graph representation of the prerequisites. To analyze the time complexity of our solution, we start by looking at the process of building the graph. This involves iterating through the prerequisites list, where each prerequisite is represented as a pair of courses, dest, src. For each pair, we add the destination course to the adjacency list of the source course and increment the in-degree of the destination course. Since there are prerequisite pairs, this step takes time. Each operation, such as adding to a list or updating the in-degree, is an O(1) operation in Python. Next, we initialize the queue by iterating through all the courses to find those with an in-degree of 0, which requires one pass through the number courses array. This takes V time, where V is the number of courses. These initial steps lay the groundwork for the algorithm and contribute OE and OV time, respectively. Once the graph is built and the queue is initialized, we proceed to the topological sort process. Here, each course is processed exactly once, meaning we remove it from the queue and add it to the result list, which takes OV operations in total. Additionally, for each course, we iterate through its neighbors in the adjacency list to update their in-degrees. The total number of edges, or prerequisites, determines how many times this iteration occurs across all courses. Since there are edges in the graph, iterating through all neighbors takes OE time. Combining these two components, the topological sort process has a time complexity of OV plus E. When we sum up all the steps building the graph, initializing the queue, and performing the topological sort, the overall time complexity of the algorithm is OV plus E. This is optimal for solving a graph-based topological sort problem. The space complexity of the solution is determined by the data structures we use. First, the adjacency list represents the graph and stores edges, where each edge corresponds to a prerequisite pair. This takes OE space. Then, the in-degree array stores one integer for each course, which requires OV space. The queue, used to process courses with an in-degree of 0, can hold all courses in the worst case, consuming another OV space. Finally, the result list, which stores the topological order of all courses, also requires OV space. These components, adjacency list, in-degree array, queue, and result list, combine to give a total space complexity of OV plus E. Summarizing the space complexity, the total is OV plus E, as it is dominated by the adjacency list, in-degree array, queue, and result list. Now, let's examine the algorithm's behavior in different scenarios. In the best case, where the graph is a simple chain, such as 0-1-2-v1, the algorithm still processes all nodes and edges, so the time and space complexity remain OV plus E. In the average case, where the graph has no specific structure, the algorithm's efficiency remains consistent at OV plus E, since it iterates through all nodes and edges. Even in the worst case, which involves a dense graph like a complete directed acyclic graph, the algorithm processes all nodes and edges, maintaining the same O, V plus E, complexity. This consistency across best, average, and worst cases highlights the efficiency and scalability of the algorithm. When comparing this algorithm to a brute force or naive approach, the efficiency becomes even more apparent. A brute force method would generate all possible course orders, which requires O, V time, and then check each order to see if it satisfies the prerequisites, which takes O, E time per permutation. This results in an infeasible time complexity of O, V. *E, 4 large values of V. In contrast, our algorithm leverages a graph-based topological sort to reduce the complexity to O, V plus E, which is far more efficient and practical. The mathematical justification for this is straightforward: each node is processed once, contributing O, V, and each edge is processed once, contributing O, E. These contributions are additive, leading to a total time complexity of O, V plus E. Similarly, the space usage is dominated by the adjacency list, in-degree array, Q, and result list, all of which add up to O, V plus E. This demonstrates the algorithm's optimality for solving the problem efficiently. When solving the course schedule 2 problem, there are several common mistakes to watch out for. First, it's crucial to check for cycles in the prerequisite graph. Many assume the input always forms a valid directed acyclic graph, or DAG, but if a cycle exists, it's impossible to determine a valid course order. This must be handled explicitly in your solution. Next, edge cases are another frequent source of errors. For instance, what happens if there are no courses when number courses equals 0, or if there are no prerequisites? Similarly, a single course with no dependencies is a special case to consider. Another common pitfall occurs when implementing DFS for cycle detection. Without properly maintaining both a visited set and a rec stack to track the recursion stack, your solution might produce incorrect results or even run into infinite recursion. Additionally, the way you represent the graph matters. Using a dense adjacency matrix for a sparse graph can waste memory, so an adjacency list is usually the better choice for space efficiency. Finally, remember that topological sort is not just about visiting all nodes, it's about respecting the prerequisite constraints. Returning an order that violates these constraints would render the solution invalid. Now, let's focus on some key insights to keep in mind during interviews. At its core, this problem revolves around topological sorting, which can be implemented using either Kahn's algorithm with BFS or a DFS-based approach. It's important to ask clarifying questions to the interviewer. For example, you might want to confirm if the prerequisites are guaranteed to form a valid graph or how to handle cases with multiple valid course orders. When choosing between BFS and DFS, each has trade-offs. While DFS is often simpler to write, Kahn's algorithm is iterative and typically easier to debug, as it explicitly tracks indegrees and processes nodes with 0 indegrees. Be prepared to discuss the time complexity of your approach. Both DFS and BFS achieve a runtime of O, V plus E, where V is the number of courses and E is the number of prerequisites, so make sure you can explain this clearly. Additionally, this problem connects to several related challenges. For example, Course Schedule 1, or LeetCode 207, focuses on determining if it's possible to complete all courses. Other variations include Course Schedule 3, which involves minimizing dropped courses, and problems like alien dictionary or sequence reconstruction, which also rely on topological sorting in different contexts. Finally, let's discuss some alternative approaches and key patterns you should know. The DFS approach with cycle detection is a robust option, especially if you're comfortable with recursion. It allows you to detect cycles and perform topological sorting in one pass. On the other hand, Kahn's algorithm, which uses BFS, is often more intuitive to debug. By tracking indegrees and processing nodes with 0 indegrees iteratively, it avoids recursion and can be easier to manage. While brute force or backtracking methods are theoretically possible, they are highly inefficient with O(n) complexity, making them impractical for larger inputs. However, understanding why such methods are suboptimal helps highlight the efficiency of topological sorting. Looking at patterns, cycle detection stands out. Many graph problems, especially those involving validity checks, require detecting cycles. Dependency graphs are another key pattern, as they are central to problems involving scheduling, ordering, or prerequisites. Lastly, always ensure you handle edge cases like empty inputs, single-node graphs, or disconnected components. These situations often reveal gaps in your solution and are critical for writing robust code. Great work! To recap, we solved Course Schedule 2 by leveraging topological sorting, which is a critical concept for dependency resolution problems. Remember to practice graph traversal algorithms like BFS and DFS, as they're invaluable tools in your coding arsenal. Thank you for joining, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!